Okay, I haven't been briefed on magic signals, so I'll just get started. So hello everybody, I'm Herman Venter. I'm a software developer in the Research and Software Engineering group in Microsoft Research. I guess the software developer part of my title is a little bit misleading, because I'm really a compiler developer. If you come to me with any problem, it doesn't matter what it is, I'll listen to you and I'll say, well, what you need is a compiler. And I've been at this for 30 years. And so along the way, you kind of notice that from one compiler to the next, there are some things that are in common. And so what I want to talk about is a library that I've put together for trying to abstract out some of these common parts and make them available, that you don't have to rewrite them every single time you write a compiler. So what's in common? So actually, compiler front ends, and when I say I'm a compiler writer, I mean I write the front end stuff. My world stops at IL. After that, there's a JIT guys problem. I don't even know what they do. But so front ends deal with different languages and different problems, and they're really very different, but they do solve the same kind of problems. And it's not just front ends. We have all sorts of other tools: designers, visualizers, profilers, debuggers, extended error checkers, a whole lot of stuff that all deal with languages and compilers in some way. So if you know how to look, everything looks like a compiler. So now it's demo time. And the challenge of the demo, I'm going to demo two tools, and I want you to spot what is similar between them. And we'll start with something really classical, C. So if I can drag this over here. So here what we have is good old C. That is just C. And it doesn't do anything very exciting. It does a linear search, and it doesn't look very complicated. How many problems can there be with something like that? Well, if you give it to the C compiler, it'll tell you, well, nothing much at all. Let's just get the C compiler up, and that doesn't want to move. Here we go. So if we could give it to the good old Microsoft C compiler, it's going to say, okay, that's fine. Well, quite happy, no problems. Then on the next line here, we have this thing calling itself VCC, which is sort of like short for verifiable C compiler. We don't mean we verify the compiler, but rather that the compiler verifies your code. And we'll see that the compiler actually has a lot of issues with that code. And it's telling you at least 3 ways in which that code can go wrong. And we don't need to go into that too very much. Just look at what this, if you want to shut the compiler up, your program becomes just a little bit longer. And this is the kind of stuff that you need to know a little bit what you're doing. So the context of the project that the Microsoft has a little operation called the hypervisor, which is a virtual machine monitor. It's about under 100,000 lines of code, of C code, and we have a bunch of very smart people, mostly in Germany, sitting there and figuring out how to actually prove that this thing is correct. And this is a highly concurrent piece of code and so on. And they end up writing stuff like that, and it goes into a verifier and a modulo checker and stuff, and all sorts of weird stuff happens. But in the end, you still have to, there's stuff there that the C compiler never sees. So all of this requires and ensures and invariants and stuff. Those are just macros. And when the C compiler gets to them, they're just gone away. They're just not there. But somebody needs to look inside those things and make sense of them and do something with them. And so that's sort of like the classical part. Now we're going to get something else. We're going to get Kale up here, and he's going to demonstrate something altogether different. But just to set him up a bit, the basic problem is this. We have a bunch of C# code here. You've never seen this before. And you want to make sense of it, just, okay, well, what's there, and so on. And so, well, you've got the solution explorer, you've got the class view, you've got the object browser, but doesn't really say anything really very much. And so Kale is going to show off a tool that he's written that gives you just a whole different way of looking at things.
Thanks, Herman. So I'm also in Herman's team, somewhat a distant relative, and I work on a project called Code Canvas, which is a visualization for code. So rather than seeing all your code in tabbed editors, we're experimenting with what would it look like if you could see all your code at once, all on a big canvas. So here's the same solution that Herman just showed you, except for you can also zoom all the way into source code, and you have code editors. And then you can zoom back out, and in order to do this in a nice way, we have to know a lot about your code. So for example, if you notice as we zoom in and out, certain things stay visible. So like this label for the class name, and then it's private fields and that sort of thing. So there has to be a compiler backend going on there. Furthermore, we have to do resolutions. For example, one of the features is you click on something like a type name, and it shows you all the places that refer to it. Here's a place that is referred in 2 spots. So this also requires resolution, and so not only just a parser, but a full compiler. You can do other things with this, like rather than grouping by folders, you can create your own custom groups so that you can actually keep track of maybe architectural intent. So here I could say, I don't want those to be viewed by folders. Oh, I only got 2 of them. I want to be in a group instead, and this persists. So that you can organize your code, and then we have a graph layout engine that keeps it all fairly organized. So part of the way that graph engine keeps it organized is by basing the layout on inheritance of classes within the file. So these little arrows are just class diagram arrows that is showing inheritance. And so that's yet another reason we need a compiler backend. And then, of course, you need syntax highlighting and all the other more fun, pretty stuff. Then another thing you can do just to show off is you can view execution traces and search results. So for example, here's the main function of a program, and if I slide this timeline across, you can see it make its way through the program and call into different parts of the code. So there's lots of different things you can do in this space, but none of it would have been possible without a back end like Herman's. Thanks.
Okay, let's see if we can get the PowerPoint back. Minimize. Okay, so we've set this, but we can just go over quickly again. So basically, you can hardly imagine two very different things from sort of like a verifier for C, and sort of like all this whiz-bang architectural viewy kind of stuff. But basically, under the covers, both these systems, never mind how different they are, still have some similar problems. They have to parse files, they have to present the source things, they have to bind names, they have to import metadata from libraries, they have to do overload resolution and type coercion, all of that stuff. So there's a lot of stuff that they do that's similar. And so CCI, the Common Compiler Infrastructure, is an attempt to say, well, let's try and package up all of these things you do again and again, the same thing, as a set of libraries and make it useful. So what can CCI do for you if you're a compiler writer? So never mind how different your compiler is, if you want to run code on .NET, and I guess you all do, at some point you're going to have to take all of your source files and scrunch them up or do something to them and produce a portable executable format file containing a .NET assembly or a module. And that's what you're going to run. So every compiler has this problem. So of course, solutions exist, otherwise they wouldn't be compilers. And so typically, and I don't expect you to read this just to be overwhelmed by it. So one solution, particularly if you are an unmanaged compiler, is to use this interface iMetadata emit that does some work for you. And it goes on, there's actually more there, and that's just the one interface. There are more. And if we drill down into just one particular method in that thing, if you are a compiler written in the managed code, there's a couple of challenges here for you. So the one is, well, there's a string there. So if you're going across interop, you're marshalling a string across interop, and believe me, that's bad news. You don't want to do that. And then there are these funny, there are these funny names and things of, very informative type D word, and it's full of bits, and you have to know what those bits do. So there's a lot of stuff you have to know. If you think figuring out what the bits are is bad, try figuring out what that guy is. That's a whole language in there, and you have to just provide some bytes that somehow mean something there. And iMetadata gives you no help. And of course, that thing gets marshaled as well. So performance is not great. So to sum it all up, if you're dealing with iMetadata emit, you've got a chatty interface crossing COM interop. Lots of marshalling going on. You have essentially an unfriendly interface for any compiler that's not written in the managed C++ or unmanaged C++. So slow. It's a bug farm. Just don't go there. Okay, so at one stage you probably were told, well, we've got this great API called system reflection.emit. And as you can notice, the API here is a little bit bigger than the one we've seen before. And there's more. There's more. Well, actually, there's lots more, but it gets kind of tedious at this point. So what's going on? Okay, so one way to put this is that iMetadata emit, system reflection.emit, does a lot more for you than iMetadata emit does. Operates at a higher level of abstraction. But unfortunately, this abstraction hides some necessary details. So you can't do everything with reflection emit that you want to do. And under the covers, it still uses iMetadata emit. So you're still paying for all of those interop penalties. And if we say slow, we mean really slow. That's why this is now a snail. This thing is just, it's terrible. So, and it's complicated API, so it's a bug farm. Just don't go there.
Can you give one quick example of a hidden necessary detail?
No. Ask me afterwards and I'll come up with one, but no, I don't have one in my pocket. So now let's look at the CCI interface for emitting metadata. That's it. That's the interface. It's one call. Right? So we're talking simple here, right? It's not what we've seen before. It's flexible. Basically, all policy decisions are provided to the metadata writer through this host abstraction. And it's flexible because you don't have to write to a disk file or something like that. You just hand it a stream, and it's a stream to anything, and it'll just zap the stuff in there. And if you want it on a disk, fine, you can put it there. If you don't want it there, then that's fine too. So it's all up to you. It's fast, no interop. You go straight to the stream, all managed code, and then from there you can go to where you want. So it really, really is much faster than the other solutions. And it's complete. So you can set every single bit in an assembly that you want to set. So if it's not constant, you can set it. So, okay, I'm cheating. You got me. I'm cheating. So obviously, there's one call to emit that module, but you have to supply this little object of this interface iModule, and that object it takes a bit of work to construct one of those. But notice it's iModule. It's an interface. So if you have a compiler, you can provide your own implementation of this interface. So if you have a whole bunch of data structures and objects and stuff lying around, you don't have to go and construct yet another object model. And that's essentially the problem of reflection emit, is that it has a bunch of factory methods, and you have to reconstruct the world as it sees fit. You can't provide your own implementations or own classes there. Here, it's just an interface. You decide how that's implemented, although there is some help as well. So it's much more flexible than the factory approach. it certainly can be less work. I mean, if you're doing a new compiler and in terms of the amount of code you have to write, it can be less work than using the factories. And if you know what you're doing, it should be more efficient, definitely more efficient. Okay, so now I just want to do a sort of like a quick survey of what's there so that when you go look at it, you can find your way around. So at the root of this all, we all know assemblies. And an assembly, as we know, is just a .NET module that has a manifest. And this is slightly generous to the idea of there's just some unit of metadata. And this is the root of a non-extensible object model. So this is an object model that specifically just models .NET metadata and IL. There's nothing, it knows nothing about C#, knows nothing about F#, it knows nothing about your language. It's just a model for .NET. It's strictly interfaces. The interfaces are strictly read-only. So there are no arrays coming back from this interface that you can mutate and then that you have to worry about somebody mutating. The objects implementing these interfaces are expected to be immutable. So basically, if you get an I module, it's not going to change under you. It's going to be the same. Every time you go to that property and ask for its value, you're going to get the same value. It's got to be thread safe, so you can throw lots of different threads at it. It's just an immutable data structure. You can go wild. Given a unit of metadata, you can start with a namespace root and traverse the thing, not just as this flat list of types that you get from a .NET assembly, but actually traverse it the way the namespace view that is sort of like more closer to what languages look like. So namespaces can contain types, and after that, types have fields and members and methods and things, and methods have bodies, and bodies have instructions, and the instructions are modeled just as a list of IL instructions. Now, in this level of the world, once you have an object model, once you've said, okay, so this is my object model, this is what I work with, turns out there's a lot of things you can do. So compilers have to import metadata. And so, well, you can just provide a reader that will take a .NET assembly and read it in and provide you one of these object models. And now your object model, the way you deal about imported metadata and the metadata that you export, that's the same. Exactly the same. It's just interfaces. But the reader, because these are just interfaces, can have an implementation that is very lightweight and specific to reading from a precompiled .NET assembly. Doesn't have to have a general representation of anything. And so importing metadata can be very lightweight, can use a lot less memory. Okay, so since this is a bunch of interfaces, you can get more implementations. So, well, you may as well just make up just a standard implementation of these interfaces and make them, give them proper getters and setters and stuff so that it's mutable. So you can make up get another implementation, a mutable model. Now you can start thinking about things like reading in an assembly and then rewriting it by systematically traversing the original model and then deleting stuff or adding stuff or changing stuff. So you can do sort of like post-compilation rewriting steps. And this is all supported by the idea of visitors, traversers, and mutators. So essentially, unlike reflection, system.reflection, every node in this, every interface in this model supports the notion of dispatching a visitor. So there's a dispatch method there and an iVisitor interface, and you can throw in the iVisitor and it's going to call the right overload on it, and then you will visit the thing. And there's a default base class implementation of the visitors that will actually traverse your object model for you. So if you just want to go find particular things, you just have to override one or two methods, and you can traverse the whole assembly in all of its gory details with all the things there, and you can just go look, oh, I want to find all references to assemblies from methods called foo or something like that. You can do that very easily. So over and above the basic object model for .NET assemblies, well, whenever you have a PE file. Typically alongside it, there is something called a PDB file, your program, your debug information. So there's another object model, which I just call the source model. It's basically just a model for saying, well, how you can relate IL instructions or IL locations back to source locations. And then there's ways to read PDBs as this model and a way to write out this model as a PDB. And so with these things in hand, you can basically take compiled code and do stuff with them, rewrite them. And you can create stuff and you can read stuff and you can basically do anything you like with the .NET assembly. Create it, change it, read it, do all those things. Okay, so the previous stuff I had in green because that's pretty stable. It's mostly, it's fairly widely used. It's mostly working. You can sort of like hope to use it and do what you want and not run into too many bugs. The color here changes to sort of like somewhat more, well, here expect to find rather more bugs and stuff that's just missing and so on. But so here we get to the point of saying that, well, okay, a flat list of IL instructions is only going to get you so far. When you're a compiler or even when you want to do some sort of static analysis or rewriting on an assembly, you really want to look at your IL instructions in the form of statements and expressions. And so here we sort of like in the code DOM land. So there's an accompanying object model for statements and expressions, which I just call the code model. Again, it's just a set of interfaces, and you can implement it any way you want. Like with the metadata model, this is a fixed, non-extensible object model that is basically just a reimagining of IL as expressions and trees. So there's enough there to represent everything in IL, and it tries to look familiar, so it looks kind of C-sharpish. But that's it. It's not an open, extensible object model that you can add stuff to. It's a well-defined meaning. So when you look at one of these things, you know exactly what it means. It has just one meaning, one form. It's just basically another way of looking at IL. To make things a little bit easier, though, it does have one or two things that's not directly in the IL. It's sort of like that's in the IL, but in a form that's very hard to work with. So, for example, if you have an anonymous delegate, what happens in C# is that under the covers it generates a class, has some fields which are which of things, and there's all sorts of mapping going on and stuff. And yeah, it's kind of that's a lot of things lying around in different places. You just want to see in a method. So. In the code model, there's basically the notion of there's a node, there's an expression for an anonymous delegate, or closure, or whatever you want to call it. And so there's a bit of mapping going on there. So there's actually a subset of the code model, which I just call the normalized code model, where these higher level mapped constructs are not present. And then there's a decompiler and a compiler. So a decompiler will take a .NET assembly and present you with a code model. And the compiler does the opposite. It'll take a code model and give you the IL stream. And there's also an IL generator, which is pretty much like the system.reflection.il generator that you can use to generate an IL stream from a compiler. But it takes care of things like labels and using the long and short forms of things and so on. What are we doing for time? Okay, so then there's the scenario where you want to start with source files now, right? There's all of these .NET, looking at .NET as compiled .NET assemblies in a particular way. But so if you want to start with source files, well, the library has some things, some green, some yellow, some red. And the red means, well, you're guaranteed to run into bugs. It's just incomplete, it's buggy, right? So there's a source file abstraction. So there's base classes that deal with streams, and particularly the problem of being able to process your input just a little bit of a time. So when you have a compiler and somebody throws a 100 megabyte long generated source file at you in Visual Studio, and they want to browse around it and get IntelliSense, you don't get to read in the whole file as one string. So there are classes that try to help you with that. And there are abstract syntax tree base classes. So abstract syntax trees, that's what the parser produces. And ultimately, that's what you're going to process and run over and do some semantic analysis and some decoration and stuff. And so there's some base classes that you can augment and extend with your own ones. So this is an extensible thing. This is something that you're meant to customize to look like your language. And then what these base classes do is they do projection. So basically, the parser builds up one of these abstract syntax trees, and then you can walk it as if it's a code model. So where it's the restricted, language agnostic, it has one meaning only view of the world. That is a .NET assembly. And so any language can go in, and the same old .NET language comes out. So you can have, if you're going to write any sort of tool that is language agnostic or language independent, you can target this standard code model. And there's this projection process that goes on. And the projection process takes care of name binding, overload resolution, all that good stuff. And it may come as no surprise to you that one of the reasons I started doing this library was system.codom. So I was doing the JavaScript.NET compiler, and JavaScript.NET is not C#. And we had to deal with the codom. And that was, I feel your pain. So the other important thing that this framework helps with and tries to give some guidance on is the whole problem of incremental updates. That you are loading in 50 projects into your big solution, and you have big files, and you have 20 or 30 files open, and now you type one character, and now you want... The world has changed, but you want to have a response just like that. Here's your drop-down list, or you've made an error or something like that. So what you need to do is you need to update your state of the world incrementally. And the basic problem is, so I just told you, look, this code model, this is immutable. It's read-only. It never changes, right? Yet every keystroke, we need to have a new one of these models. And so that's a bit of a problem. And so the framework tries to help you out, suggesting a way that you can do that efficiently. So some miscellaneous things. So there's the notion of a host object. So basically the compiler or the application hosting the compiler or whatever gets to implement the host interface, which basically means that whenever a decision has to be made as to how you do resolution, which target your platform, where you get your options from, how you do this, how you do that, it always calls back and says, okay, well, you tell me. Yes, we're running out of time. Okay, so things like unification. When you have different references to the same assembly, different versions of that, which one do you take? How to go cross-platform. One of the things that this object model does differently from system reflection is that whenever you reference something like a type or a method, you have an explicit object that says, I am a reference to a type, instead of just the type itself. And this really helps with things like generics. And most importantly of all, interning strings. So most of the API doesn't have anything to do with strings. When you get all of a string in the parser or whatever, first thing you do is you go and you intern it, and you get back an iname object with a nice integer key that is unique. And from then on, you just work with this nice object and integer, and you need never do string comparisons and string this and hash of strings and so on. And strings don't cross-interrupt, and you don't pass them around and copy them and do stuff like that. Okay, now hopefully the nice part of this. This is all open source. As of yesterday, this is on CodePlex as a Microsoft public license or permissive license. I don't know which is which, but the PL. The one that says you can take this code and you can do with it whatever you like. Right? And what I would like is that you would take this code, do some nice stuff with it, and put it back there so I can do with it whatever I like. And not too many of us are working on this. This is not a product team. This is a research effort. So it's kind of the open source model where, we're giving up some valuable stuff, we hope. And in return, hopefully everybody else will give up some valuable stuff. There was going to be a sample C# 2.0 kind of compiler, but we ran into some legal difficulties and it's still being worked out, and hopefully something will happen there in the next month or 2 or 3. And I look forward to seeing your CCI project showing up on CodePlex. So I don't know if I talked about this. Maybe I shouldn't say, well, I just want to remind you that perhaps I'm a snake oil salesman. Yeah. There definitely are some dangerous areas here. There's a lot of stuff under construction, and I have a hammer, so everything's a nail. So just be aware of that. Lots and lots of stuff that remains to be done. The classical thing, testing. Documentation, some of the stuff we're working on, but there's ample scope for contribution. And final message is, I need you. Thanks.